Can't really see if it'll cover the whole board. That's okay. All right. So last time we started our discussion of multiple regression. True? Okay. And just to refresh everybody's memories, you probably already have this in your notes. To refresh everybody's memories, what we want to do is we want to be able to build a predictive model to predict some kind of outcome. But we don't want to be limited to a single predictor, right? We know that oftentimes out in the universe, there are going to be many things that might add together, right, to form some kind of better prediction of some outcome, right? So we might have some intercept, we might have some slope associated with some with some independent variable, and then we may have, I did this in a different color last time, that'll be a good idea to do it here too. And then we may have additional slopes for additional random variables, right? All the way to some pth independent variable that we might include, right? Well, to do that, losing my voice. To do that, we need to have linear algebra because we have to work with this system all at the same time. We started to tee this up last time. Hopefully my voice lasts. So to do this, to do something like this, we are now going to have a vector. What this little notation means, we're now going to have a vector of y's, right? A vector of y's, right? Where every person is going to have a y. Every person is going to have a y. I'll try and make this consistent. So the first person's, the second person, dot, 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 right? The ith person, dot, 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 the nth person, right? Where this is y1, y2, dot, 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 some as of yet specified yi, all the way down to some as of yet, well, if we specify n, whatever the last person on our data set is. So far, so good. So this is a what vector? Dimension-wise. Yeah, it has n rows and one column. So it is an n by 1 vector, right? Okay. Then we have some x matrix. And this matrix, I might need that space in here. This matrix starts with a list of ones. We talked about this last time. I'll talk about it again in just a moment. It starts with a list of ones, okay? And it ends with, well, we'll talk about what it ends with in just a moment. So these are ones all the way down, dot, 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 1, okay? All ones. And then this will be the x score. This will be the x score, sorry. This will be the x score for person 1, that is associated with the beta 1 slope. So we'll call this x11. We'll call this x11. Okay. Now, this is a crucial piece of what's going to make this a little tricky. Not tricky like I don't get it, just tricky I have to hold this in my mind. Notice that x11 is not the first element of the X matrix. Okay. At some point, I will talk about the first element of this matrix. And when I do that, I will try and be very clear and say X where I is equal to 1 and J is equal to 1. Okay. People with me? I know it's weird. There's really no good way to notate this, at least not that I know of. That's why I'm doing it this way. Okay. So the first, we'll do it this way. The first index here does correspond to the ith person, okay? But the second index here corresponds to the beta it is associated with. People with me? Okay. So we're going to have a matrix of this. We're going to have a full matrix of this, right? This second one is going to be x1, 2. right? The third one will be x1, 3, dot, 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 right? Eventually, we will have x1, p, right? Because we will have p independent variables. So this is our X matrix. Okay. We're also going to have some beta vector. Today I'll try and use capital B. I know I was switching up a whole bunch last time. Sorry about that. I'll try and be consistent. So we have some beta vector. Okay. This is made up of your intercept, beta naught, your intercept. Again, sorry, I wrote everything lowercase up there. In my hand notes, I have everything uppercase. This is the problem with math. Different books use different notation. I've read a million books, so I'm a little bit wonky. Okay, then you'll have beta 1, you'll have beta 2, right, all the way down to beta p. Okay, so this is a
N.
Say
N by 1.
Not n. It's a good guess. N tells us how many people we have.
Yes.
P plus 1 tells us how many betas we have.
These are our predictor variables?
Exactly.
Okay.
Does that make sense?
Yeah.
Right. There are p plus 1 of them, right? Where p is the end index, but we know that we started at 0, right? So you got to include 0 in the total size. So p plus 1, right, by 1. That is a p plus 1 by 1. Whereas this matrix, notice that this matrix includes people, and it also has a variable ready to be associated with the betas. So this is a n by p plus 1 matrix. People with me? Okay. All right. So our job, very, very similarly to what we were trying to do when we were working with the bivariate case. Our job is to somehow, oh, I didn't write the very last thing here. I know I did last time. Okay, but let's talk about some E vector. Okay, this is a vector of E1, E2, dot, 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 En, right? There's an error term for each person. Okay, and last time I remember doing it on the far side, so you'll forgive me if I don't do it again. Okay, but hopefully everybody is comfortable now with the idea that if I write E transpose E, that is the same thing as saying the sum of the squared error terms. Agreed? Okay, we did that demo last time. So this is what I call my residual sum of squares, right? It's now just in matrix form, in this case vectors. Okay. So our job is to minimize this, right? Remember in the bivariate linear regression case, our job was to minimize the residual sum of squares. We wanted to find the equation that did that. Well, it's the same thing here. We want to find the equation that will minimize that. Just that now the algebra we use is linear algebra. Okay. Now the algebra we use is linear algebra. So I'm going to go through this. I'll try not to go too fast because, again, calculus, people have different levels of preparedness with. The ideas are the same. Right? This is a function. We are looking to find the smallest value of this function and extract from it the betas that got us there. That's what we're trying to do. So we want to minimize this thing with respect to the beta vector. Okay, this is called vector calculus. Okay, because we now have an entire vector of betas with which I want to minimize this thing. So in math terms, it really doesn't want to erase, does it? In math terms, what I would write is I want the derivative with respect to beta, the beta vector of E transpose E. That's what I want. Okay. Let's just take a bit of a segue and think about, well, maybe you guys don't know this, so let me take another step back. When we do vector calculus, the result is a vector. So the result will be a vector of length, however big beta was. Okay. So we will have a vector of derivatives. one for each of the betas. One for each of the betas. Okay, that's how it works, right? You have this entire vector, you pass in each one to this, and you ask, what is the derivative related to this? What is the derivative related to this? What is the derivative related to this? Right? So you get an element in your resulting vector of derivatives for every beta that you pass in. Okay, people with me? Okay, yeah, I will try not to go any deeper than that, so long as you guys say this. Okay, all right. So let's just think about for a moment. Let's do well, it'll actually be for a long time, but instead of thinking about all of the betas at once, let's think about what's going on if we fix our gaze on a single beta, call it beta k, okay? Could be the first beta, could be the pth beta, okay? But just one of them, okay, with me? Okay, so we're just looking at, right, we know the result is going to be a vector, right? And it's going to have 1, 2, ... It's going to end at p. We know that, okay? Because it'll have the same length of the beta vector, right? What I'm saying is let k index the entries of this vector, right? So that as I say, hey, the kth one, right? That could be anywhere between 1 and p plus 1. Okay, so just generally the kth. Okay, so if we're talking about the derivative with respect to beta k, okay, then we're asking, hey, what is the derivative? What is the derivative of E transpose E for a single beta k? Okay, that's what we're asking. And we have to remember that this entire thing is the sum of EI squared, right? That's what E transpose E is. Okay. So what we're doing is we're bringing this back to a scalar form so that we can sort of see what's going to go on in the matrix, in the vectors. Okay. All right. So I'm now asking, what is the derivative of this thing, right? I can rewrite that. Sorry, try and be consistent. I can rewrite that as this. So if I substitute my definition of EI, okay. Sometimes I write this, sometimes I don't. I'm inconsistent. Okay. If I substitute my definition of EI is simply equal to somebody's actual YI value, right? Minus, and this is where we're going to have another sum, minus the sum of, and I'll talk about this, I is equal to 1 to p plus 1, minus the xij minus beta j. Let me think about that. That minus shouldn't be there. Sorry, 1 second. Well, actually, yeah, it is. It is. It just depends on if I've distributed yet. So let me not distribute yet. Sorry, people. 1 second. No, I don't know why I have a minus there. It should be a multiple. It should be a multiple, but I need to fix these lines. That's okay. So let's think about why this is true. Let's think about why this is true. So what an individual error term is, right? What an individual error term is somebody's actual yi value minus yi hat. Yi hat, right? We know this from bivariate linear regression. Okay. Well, what is yi hat? Yi hat is quite literally beta naught plus beta 1 x1 plus beta 2 x2 ... plus beta p xp, right? That's what yi hat is. Agreed? Okay, so let's think about this expansion. This says start at the first I, go to p plus 1, and take all of the xij's and multiply them by the bj's. Okay, if you expand that, the sum of I is equal to 1 to p plus 1 xij multiplied by beta j. Okay. Notice that this is for a fixed I. Sorry, let's be smart. So sorry, I meant to do this. This is for j, not for I. This is for j. We already have an index of I. I can't reuse I. I did it here, but I forgot to write it there. Sorry to confuse people. People with me again? Okay, all right. So what we're trying to do is we're trying to say, okay, I've got this summation, right? This is all happening inside of this other summation. So at any given time in this summation, we're going to have an I that is fixed. We're going to have an I that is fixed. It'll start with I is equal to 1, and then all this will happen. Then it'll happen again for I is equal to 2. But at any point, I will be fixed while we're going through j. Okay? At any point, I will be fixed while we're going through j. So let's think about that, right? Let's just pick an I out of the of our hat. Let's start with I is equal to 1. Okay? So let's let I be equal to 1. Okay? If I is equal to 1, that's a 1 right there. Okay? So what is this going to be? Well, this is going to be the sum starting from j to p plus 1 of all of the stuff between, or multiplied between the x and the b. So if I plug in j is equal to 1, I get x1, 1 multiplied by beta 1, right? And just to be totally clear, I promised I would do this, so I will, right? This is where j is equal to 1 multiplied by beta, where j is equal to 1. Okay? And I need to add to that x1, where j is equal to 2, multiplied by beta, where j is equal to 2, right? I need to add to that the next one, which is my third one, and I'm going to keep adding those until I get to x1, p plus 1, right? Multiplied by beta, where j is equal to p plus 1. Okay, and what are those? Well, they're nothing else but these elements, right? X, where I is equal to 1 and j is equal to 1, is just this 1 right here. People with me? Right? So that's equal to 1 multiplied by, and beta, where j is equal to 1, is just this beta naught right here. Okay. So that's 1 multiplied by beta naught, right? My next term is simply going to be whatever that x over there is, where j is equal to 2. So that's xi 1, which I know gets confusing. That's my xi1 right there. Did I lose you there, Josh? Okay. Multiplied by beta 1. Agreed, right? And we're just going to continue until we get to my x1p multiplied by my beta p, as we should. Agreed? That is the definition of why I have, right? And it's the definition of this stuff inside of here. Okay? So when I'm taking this derivative, all I'm saying is that I haven't changed anything. This is the same thing as this.
What happened to the squared?
Thank you. You're right, Josh.
Okay.
Thank you. You're right. Now it's the same thing.
Got it.
Agreed? Now it's the same. Okay. So we expanded that out, which is good. I wanted to do that anyway. So we can see that if I take the derivative of this thing, with respect to a specific beta, okay? There's this thing in the chain rule, or this thing called the chain rule in calculus, which tells us that, well, it won't affect the sum. Derivatives are linear operators, so we can just stick it right inside of the sum. So the sum's going to be fine. Okay. The very first thing that's going to happen is chain rule. Chain rule says, okay, take this entire squared stuff, bring down the 2, and rewrite what was inside of that function. So my very first term here, is going to be 2 multiplied by yi minus everything that I already had. No change. Okay. Except that now it's not squared. Now it's not squared. Okay. Okay, chain rule again. So that's the first step of the chain. Second step of the chain rule says, okay, now take the derivative of the stuff inside of that function. That function was a square. Okay. So what is the derivative of this stuff inside here, which we've expanded over here, right? What is the derivative of that stuff with respect to a specific beta? With respect to a specific beta. Okay. It's again, it's derivative calculus. Okay. But this is like one of the basic forms of derivative calculus. Differential calculus, I guess, is the better word for it. Okay. If I were looking at this thing and I were looking at it with respect to beta naught, if I were looking at it with respect to beta naught, I see people still writing, so I'll pause for a second. Everybody with me now? Okay. So what I'm doing, look at this, right? This is the expanded form of what was on the inside, right? This is that expanded form of at least this summation, right? We can ignore the yi for a second. Okay, this is that expanded form of the summation. Okay, among these terms, if I'm taking the derivative with respect to beta naught, if I'm taking the derivative with respect to beta naught, what we have to do is we have to look at each term and see, does it have a beta naught? If it has a beta naught, then we can take its derivative with respect to beta naught. If it has no beta naught, its derivative with respect to beta naught is 0. It doesn't change as beta naught changes. Okay, does that make sense? So what that means is that every single one of these terms that doesn't have a beta naught will be 0. The only one that'll survive is the one that had beta naught in it, right? That beta naught will go down to 1. That's what happens when you take the derivative of something with a power of 1. This beta naught has a power of 1. Okay, take its derivative, it goes down to 1. You end up with 1 multiplied by 1. That's the only thing that comes out of this. Okay, if we were doing this for not beta naught, but for beta 1, the only thing that would come out of this would be this x11. Okay, if it was beta 2, the only thing that would come out would be this, I didn't write it, but it would be the x2 or x12. Okay, the point is that what comes out of it is the kth x, the x that is associated with the beta x, the beta k, can't talk. Let me start that over. What's going to come out of it is the x that is associated with the kth beta. So we're going to get the kth x. We're going to get the kth x back out. So just looking at this, the derivative of yi with respect to beta is 0. It doesn't have a beta to save its life, right? It doesn't change along with beta. So it's 0 minus what we just talked about. We're going to get the x, right? We're going to get the xi k. We're going to get the xik. Okay? People with me? We're still summing in terms of I, so we haven't done anything with the i's yet. That's still happening. Okay? We're going to get the xik. Are people with me? Okay. Sorry, just 1 second. Lost my spot. We did that. Okay, yeah. Yeah, so if we just do the math on this thing, right, people will recognize that this is just an EI. This is just an EI. It's an actual Y subtracted by the predicted value for that Y. Okay, with me, right? So if you take that EI and you distribute it over here, right? Distribute it to these parentheses, multiplication by 0 goes away, and then multiplication by a negative xik. Okay, so that's what I'm about to write. So you're going to end up with a sum from I is equal to 1 to n, and I'm just going to bring the negative up in front of a negative 2 ei xik. Okay. So far, so good. This is heady stuff, people. If you're even tentatively okay, you're doing really good. But please stop me if something I did didn't make sense. Okay. So what we've just found is that for the resulting matrix, this matrix up here, right, our derivative matrix. Maybe I can just write this to be a little bit bigger so we can see what's going on. Well, it's going to have to be even bigger than that. You shouldn't have to change your notes, but I need to change my board so I have more space. So this is still going from 1 to ... k, right, ... p plus 1. So my very first element, it doesn't have to be my first one. I'll look at the very first one, right? Say where k is equal to 1, right? This would be where k is equal to 2. This would be where k is equal to some variable k, and that's where k is equal to p plus 1. Okay, I'm just sort of trying to visualize what my result is going to look like. Okay, I know that my result is going to look like this, right? Which if I expand, right? If I expand, this is just negative 2 multiplied by e1, right? Multiplied by x, where I is equal to 1, j is equal to 1, right? And I need to add to that, or subtract from it, I should say. I need to subtract from that 2, e2, right? Because now I has gone up 1, right? 2e2 multiplied by x2, x, where I is equal to 2 and j is equal to 1, right? And that's going to go on and on and on. Should have made this even bigger. That's going to go on and on and on until eventually we're subtracting 2 e to the n multiplied by x, where I is equal to n and j is equal to 1. Right? People with me? Okay, and you could rewrite that for any of these. You'll just iterate your j's as you come down on the case. People cool with that? Okay, so that's what our derivative vector, is going to look like. That's what our derivative vector is going to look like. Okay, it's going to have that form. Now, what I want people to be aware of, right? I have one of these for each k, right? For each k. Right? What I want people to be aware of is that when I create this matrix, this vector, I should say, which is just a one-dimensional matrix in at least one direction. Okay. When I create that, I need to erase that stuff because I need to remove. What I need to realize is that I could write it in matrix form. So let's do that. So if I write negative 2 multiplied by x transpose E vector, negative 2 multiplied by x transpose E vector. Let's think about what that matrix would look like. Okay? So just sort of try and draw this out. So I get 2 multiplied by a matrix, okay? This is x transpose, right? So now its first row is a bunch of 1s, right? Okay. Its first element here is going to be that x 1, 1. Well, x 1, 1, right? Over here is going to be x n 1, right? down here is going to be x 1 p, and over here, right, dot, 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 is going to be x n p. Sorry, it's a big. Okay. That's loosely, right, I didn't fill in all the dots, but that's loosely what x transpose is going to look like. People with me? Okay. If I take that x transpose and multiply it on the right by my error vector, right, that's e1, e2, dot, 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 en. Okay. And I've also got this -2. Sorry, it's supposed to be a -2. Okay. I've also got that -2, which is a scalar. You can multiply a matrix by a scalar. I hope we covered that. If not, we'll just say when you multiply a matrix by a scalar, it changes every value in that matrix by that amount. Okay. So this is a p plus 1. This is a p plus 1 by n. Okay. This is an n by 1, right? These are conformable. Agreed? Yeah, they are. And our result will be
P plus 1 by 1.
our result will be a p plus 1 by 1, right?
Is the same as the beta.
Which is the same as this, right? So far so good. Okay, at least we have the same dimensions. Okay. And let's think about what our elements are going to look like. Okay. So our very first element, right? Or we don't have to think about the first one, but I will. So let's think about our very first element. Okay. So for a p plus 1 where k is equal to 1. Okay. So it's going to be this entire row multiplied by this entire vector, right? So it's going to be, well, that one's actually kind of boring. Sorry. Let's do the second one. So this will be x11, x12, x13. I hope I did that right. Okay. Yeah, that should be right. Okay. So if we look at our second one here, right, we're going to take our x11, we're going to multiply it by e1, right? We're going to add to it x12, we're going to multiply that by e2, we're going to add to that x13. I think yeah, so sorry everybody. Yeah, I knew something was wrong. Sorry. Have people seen it? I'm indexing the wrong, I'm trying to do what I would normally do, but this isn't a transpose, right? These things are going up on the second index, right? So this one should still be x11, but this one is x21. This one is x31,
Oh, okay.
right? Because it's the transpose of my original. And that means down here, that should be okay.
Yeah, I think those dots too are okay.
I think that one, yeah, it's okay. It's possible I just read something else up. We'll go with it. So this is x11 multiplied by e1. This is x21 multiplied by e2. This is x31 multiplied by e3, dot, 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 right? So eventually we get x n1 multiplied by e to the n, multiplied by e to the n, which, if you ignore the -2, is the same thing that we had over here. If you ignore the -2, is the same thing that we had over here. Okay. Everybody cool with that? Okay. A little bit hasty, but what I'm trying to show you is that this right here is a valid matrix representation of the derivative with respect to beta. Okay. Kind of cool. Questions? Okay. So, as we did when we were working with the bivariate case, if you're trying to solve for the minimum of a function, you have to know a few things about it. For one, you have to know that there is a minimum. You have to know that it's convex or concave. You need to know this kind of stuff. Okay? But anyway, so what we need to do is we need to set it equal to 0. So we need to say 2x transpose E vector is equal to 0. Okay? That's what we need to do. Because the minimum people will remember, like, right on this board that already has writing on it, right? What we're doing is we have some function. Right? And we're trying to figure out where its first derivative, I shouldn't have drawn it the way I just did. So I don't make it look like it's too easy. What we're looking for is where its first derivative stops changing. Okay? Where does it stop changing? It's right there. Where it stops changing happens to be the minimum of this function. Okay? Where its first derivative is 0 is the point where the actual function is minimized. That's what we're looking for. Okay, so if I set this first derivative, which is this, if I set this first derivative equal to 0, it should give me what I'm looking for. People with me? Okay. I accidentally closed my notebook. I'm a pretty useless file, so I'm going to open that. Okay. So set this equal to 0, right? So we need to remember, just right off the rip, this E vector is simply equal to the, in matrix form, it's simply equal to the Y vector minus the X vector multiplied by the beta vector. Did we do that one last time? Okay.
Just what you wrote right there.
Yeah.
I haven't made notes.
Okay. We must have, but I'll just appeal logically, and I'll just say, we know that the Y vector are people's true Y scores. So that one's pretty straightforward, right? You take each person's true Y score and you subtract from it something. Okay. This something, if you just look at the math, this something is going to be individuals' predicted values, right? If you take this row vector and you multiply it by this column vector, you will get exactly this equation for each person.
That makes sense.
Okay, so this is the same thing as my E vector. Okay, so over here, I'm just going to write that out. So I'm going to, well, I hate writing so low that you guys can't see it over the board. Okay, I know what I'll do. I'll write up higher to begin with. 2x transpose E vector is equal to 0. Okay, so I'm just going to rewrite, substituting in what we just talked about. So substituting in Y vector minus X multiplied by beta vector, okay, that is equal to 0. People with me? Okay, no harm, no foul so far, right? Okay. Well, now I'm just going to do some manipulation algebraically. Okay, I'm going to distribute. So I end up with negative 2x transpose multiplied by Y vector minus 2x transpose multiplied by X multiplied by beta vector. That is equal to 0. Sorry. Plus. Negative times a negative is a positive. Okay. So far so good? Okay. So I'm just going to rearrange. What I'm trying to do is get this beta vector on its own, because I'm trying to solve for the betas that minimize this thing. So I'm going to rearrange, right? So you end up with 2x transpose x multiplied by beta vector, right? And I'm going to move the negative to the other side, because you might as well get rid of the negative while you can, right? So far so good? I don't think I lost any terms. Sometimes I do that. Okay. Right off the rip, we can see that 2 is going to cancel out. Okay. That's easy peasy. Okay. That 2 is going to cancel out. Okay. And now everything that we learned about inverses comes into play, right? There's no such thing as division. There's no such thing as division in matrices, but there are inverses. So if I'm trying to get beta by itself over here, I need to multiply on the left by the inverse of x transpose x, right? I need to multiply, I'll just go ahead and write it. So I need to take x transpose x inverse, and I need to multiply that by x beta. right? Whatever I do to one side of the equation, I must do to the other. Remember, matrix multiplication does not commute. If I multiply it by the left over here, I gotta multiply by the left over here. Okay? So now I have x transpose x inverse multiplied by x transpose y. Okay? I'm so sorry, everybody. I missed x transpose x multiplied by x transpose. Right? I forgot to write that. Confuse anybody? Okay, I just forgot it. It's right here.
Yeah.
Okay. Multiplied by x transpose x beta. Okay. This whole thing is now just an identity matrix, right? Anything multiplied by its inverse is an identity matrix, right? So you end up with the identity matrix multiplied by beta is equal to x transpose x inverse, yep, x transpose y. Okay. Truthfully, the identity matrix doesn't really change anything here, right? We talked about how the identity matrix is the matrix form of multiplication by 1, right? So in simplifying, we can just get rid of that. And we have a solution for beta. This is the matrix form. This is the matrix form of your beta coefficients. You want to know what predictors will give you the best, at least according to least squared error, the best predictions of y? That's it. It's the matrix defined as x transpose x, quantity inverse, x transpose y. Okay. If I ever get a tattoo, that'll be it. Questions? Okay. There were a lot of moving parts in what we just did. Okay. I just hope that everybody can appreciate what's happening is we have to work with all of our stuff all at once. All at once. Okay. And observe what we are taking the inverse of is x transpose x. Okay. That means that if we have a row in our x matrix, if we have a row in our x matrix or a row in our x transpose matrix that is determined by another row in our matrix, we talked about this last time, it's called collinearity, and this inverse might not exist. Okay? More practically speaking, just to get to the heart of multiple regression and some of the biggest issues you will face when you go out to use it in the wild. If you have the same predictor twice in your matrix, you will not be able to find this inverse. This x transpose x inverse won't exist. It won't exist. And that means that you cannot find your beta coefficients because they won't exist.
When would that happen? When would you find that?
The most common way that I have seen is that people will unintentionally measure the same thing twice. Unintentional. They'll think that they're measuring two different things, but they're actually just the same thing called something else, right? So maybe one's like socioeconomic status and the other one's like wealth. I don't know, something like that, right? Where they correlate perfectly. The numbers might even look different, but within some kind of multiplicative, I can't speak, multiplicative, within some kind of constant, okay? They're the same thing, okay? Right? I mean, this is a silly example, but it could be something like measuring temperature in two different systems, right? Well, you can transfer from one to the other, right? They are one to one, okay? So it happens, unfortunately. And even when they are not, this is a key feature, even when they are not exactly the same thing, they might still correlate so highly that when you ask your computer to solve for this numerically, which is what a computer does, right? It might hit some kind of ridiculous round-off error trying to solve for this thing where the determinant is basically 0, right? It may not be 0 up to 24 decimals, but your computer might run out of power long before it figures that out, and it might give up or break, right? Okay, so sometimes things that are very, very highly correlated can cause this to happen. I'll just add one more stack onto that and say, it's not just that two things might be almost the same thing, but if a combination of other things can explain one of your other predictors, then this will also happen. It's called multicollinearity. Okay. As we were seeing, when we were trying to solve for matrices, for inversive matrices, we were using our elimination methods, right? Our elementary matrix operations, right? To solve for the identity matrix, right? Well, if when you're doing those row conversions, what if you eliminated an entire row and it suddenly became all zeros? You're in trouble, right? And that can happen in multicollinearity. It may not be a single step that gets you there. Take this one, subtract from it this one. But it could be that you add a bunch of stuff and subtract a couple of other things, and bam, you've got a full row of zeros, right? So that can happen when, for example, say you have a composite variable like socioeconomic status, which might be the sum of a couple different things. I don't know all the things, it's not my area of research, right? But it could be something like parents' college graduation status, right? It could be family income, right? It could be a bunch of other things, right? If you take all of those variables, you put them in your model, and then you also put socioeconomic status in the model, which is made up of those things, your model's going to blow up, right? And that's an easy accident to make. Okay? You guys are getting the crash course in multiple regression, but honestly, if that made sense, you're doing good. Okay, these are things that happen out in the wild. People get multicollinearity and they don't realize what's going on. Okay. So let's do some R. Let's do some R.